Okay, what I want to do now in this hopefully short video is apply the density of step functions in LP to give a quick proof of the Riemann-Lebesgue lemma. And I'd like to also, on a separate topic, very quickly, just kind of dab our feet into convergence in LP and how it relates to other modes of convergence. So what is the Riemann-Lebesgue lemma? And it's probably a little hard to appreciate this. That's fine. We'll do a lot more of this in next semester's harmonic analysis course. So this simply states that if F is an L1, and if F hat, so I'll write it like this. It's a little different than it's in the prelim, than how it's written in the prelim rather. So let's say this is F of X e to the I forget if it's usually a minus or not, but I'll just make this a little simpler. 2 pi I ux x. Then the claim is as follows. And here n does not have to be an integer. This equals 0 as n goes to infinity. Okay, plus or minus infinity. Okay, so right. So what's the idea? The idea is, well, what is this? Of course, Euler's formula. This is cosine 2 pi. So let me plug in n. Yeah. So let me do it like this. This is 2 pi n x plus I sine. Again, I want u to be x. If u equals n. Okay. And the idea of graph sine 2 pi nx, or I'll put a graph up in a second. Yeah, so let's say even n is not that big. It's 5, so it's 10 pi x. So you see here you have a whole lot of positive and negative area. And so the idea is that if I integrate f of x by, let's say, sine n pi 2n pi x for n really large, no matter what f of x is, you're still going to have positive area canceling with negative area. And in the limit, as the frequencies get more and more and more, the oscillations get more and more and more, the integral, the positive area is going to cancel the negative area, and you get 0. Okay? And we make this argument at really airtight by using the density of step functions in L1, right? And the same thing for cosine, basically. Right? Okay, so yeah, what's the proof? The proof is actually very easy. So pick G, a step function. Well, first, sorry, let's, as always, not always, but we're trying to do this, let epsilon be bigger than 0. Pick G is a step function. So it's Ci times the characteristic function of AI, Bi, where these are finite intervals. Crucial for this application here. Can't really take an improper integral of sine or cosine, minus infinity or infinity. So it's crucial that these are both real numbers. All right, where this is, and I'm not going to write of R, but it's over R. Oh, this is less than epsilon over 3. All right, so sorry. So f hat of n is going to be equal to or less than or equal to just usual triangle inequality. F hat of n minus g hat of n plus absolute value of g hat of n. So actually epsilon over 2 works. Let's call this an, and let's call this, for lack of anything better to call it, bn. Okay, so this is going to be equal to, well, just use the definition. So instead of, so it's really, it's, integration is linear, so it's this with f of x minus g of x. So e to the 2 pi I and x. All right, so I smash an absolute value. You're allowed to do that. So this is trivially less than or equal to, well, epsilon over 2. Because g is picked where this is less than epsilon over 2. All right, so bn, we are just simply going to calculate directly. So literally what I said holds for bn, in the sense that you literally take something like sine 10 pi x, integrated over any interval, and you're going to have positive and negative errors canceling. And as this grows here, so sine 10 pi x, 20 pi x, 100 pi x, a million pi x, for any fixed interval, the positive areas will cancel the negative areas. And in the limit, you integrate sine 2 pi n x on any interval as n goes to infinity, you're going to get 0 because you have positive and negative areas canceling. And let's see that. That is literally just calculus 1. So this is going to be integration is linear. So this is going to be, well, I'll just write it like this. G of x e to 2 pi I and x. X. So this is going to be equal to, I'll use triangle inequality in a second. What did I put here? Hopefully I didn't put n. Okay, so I really meant m, not to get confused with the m before. I want to be clear here. What I'm doing is I'm fixing. So for every epsilon, pick an epsilon, then fix a g where this is true. Okay. So this is going to be ci. Well, it's just the characteristic function of this interval here, so it's going to be ai and bi e 2 pi I n x x. And just to make this a little efficient, this is going to be, as before, cosine 2 pi n x. So this would be less than or equal to the sum here, I equals 1 to m, ci. I'm not smashing absolute values in, but I want to integrate this. Cosine Yeah, it's not very subtle what's going on here. You integrate. When you differentiate, you pull out constants. When you integrate, you pull them out in the bottom. So these are going to go in the bottom. Again, this graphically makes sense, and it's reflected by just the positive and negative areas canceling as n goes to infinity. So this equals this is going to be so it's well minus sine. So sine 2 pi n bi minus sine, doesn't matter. These are all bounded by 1. I'll do it like this. And then same thing for cosine. When you integrate sine, it means minus sine, but whatever, it's absolute value. And just to be absolutely clear, yeah, integrate sine to get minus cosine, but absolute value, so it doesn't matter. And again, the point here is I'm just going to use triangle inequality. Everything in a numerator is bounded by 1 in absolute value. So this is less than or equal to 4. I'm only doing this in case there's any doubts of what's going on. So I'm not even, yeah, I'll do this. So let me pull out the over 2 pi n. So it's over 2 pi n. I equals 1 to m. Ci. And this goes to 0. Okay. Okay, so if you want to be really well, yeah, okay. So what we'll do is pick let's say n tilde, whatever, n bigger than n tilde implies bn. Remember, bn is exactly this here is less than epsilon over 2. You also play around with lim sups. Let's do less than. So it implies both of these are less than epsilon. So that's the definition of converging to 0. And in case you're a little curious, or in case you want to be a little careful, and I want to make sure you understand that everything is fine here, in the sense that, so what we started off with an epsilon, we picked and fixed a g where this is true. G is a step function where integral in L1 f minus g is less than epsilon over 2. All right, then an trivially is less than epsilon over 2 in absolute value. And for large enough n, depending certainly on big M, but big M depends on epsilon. So ultimately for this n tilde depending on epsilon, again, n tilde certainly depends on the coefficients, CIs, and it depends on M, but those depend only on epsilon. So this depends. Well, of course, it also depends on, to be clear, depends on F. I mean, that's kind of obvious. For different F, you're going to have different speeds of the Fourier transform converging to 0. So yeah, if I didn't say this is the Fourier transform here. But yeah, it depends on F. So no claim of uniformity over all F and L1. Yeah, so G just depends on G and thus M, and the coefficients depend on epsilon and the function. And that's that. All right, so lastly, well, let me plug in my laptop. It takes a crap on me. So lastly, on a totally separate topic, I do want to briefly talk about convergence in LP. So let's say E is a measurable set. It really works for P between 0 and infinity, but whatever. Yeah, so a little definition. If yeah, let's say I have a sequence Fn, a subset of LP. And let's say F is an LP. So we say Fn converges to F and LP. If, well, you have convergence and norm in the sense of a dog here. So this equals 0. Okay. All right, so a little proposition that's very important. It's a slight variation of Chebyshev's inequality. So if lambda is bigger than 0, then the measure, let's assume F is an LP of E. This is pretty trivial with everything we know about integration. This is less than or equal to 1 over lambda to the P times the LP norm to the P. Okay, so what's probably easiest to do is multiply by lambda to the P, both sides. So what I have is trivially equivalent to this being true. Okay, so how do we prove this? Well, this here is equal to this integral. So let's give this a name, for lack of anything better to call it. Let's say this is E lambda, or this set here. So you do kind of the obvious thing. This is bigger equal to. So I want bigger equal to here. Integrate over E lambda. It is kind of an obvious thing to do because you know what f of x is like on E lambda. So it's like Fooch here. licking her paws. Summer allergies, fun times. Yeah, so this here is bigger than lambda, well, to the p, because to the p here. So this is bigger than, it's actually less than, but whatever, it doesn't matter. This is bigger than integrate e lambda, well, just this constant here. So I pull out the constant. So this equals lambda to the p. So it's lambda to the p times the measure of e lambda. And that's exactly what we want. All right, so an easy corollary of this is the following. If I have convergence in LP, then I have convergence in measure on E. All right, so remember what convergence in measure is. This is very easy. I need to prove this is 0. I need to prove this is 0. That's my goal. That's what I need to prove. Okay. But I know, but what we just proved, that this is less than or equal to, well, 1 over lambda to the p times the integral fn minus f p, and that's 0, because you can pull the lambda out. As small as lambda might be, it's still, well, not, 1 over lambda to the p is still a positive number. You can pull the constant out, take the limit. We're assuming convergence in LP. So we're done. Or to be clear, maybe a little clearer if it's not, this equals 1 over lambda to the p times this limit. And this is. Okay, so a consequence. So one thing I have a video up for, and it's a little technical, so we're not gonna, I usually don't do it at 510A, but if you're curious, so LP is complete in the sense that if you have a Cauchy sequence in LP, then that converges to some function, really class of functions in equivalent to the equivalence class of functions in LP. So if you have a Cauchy sequence of LP functions in the usual sense with respect to the LP norm, then that converges in LP. Then that sequence converges to something in LP. Okay, well, one immediate consequence is if Fn goes to F in LP, then for some subsequence Fnk, we have Fnk goes to F pointwise almost everywhere on E for some subsequence FNK. And the proof is there's really not much to do. So this implies convergence in measure. And I don't want to write anymore, but this, I mean, for some subsequence FNK. Okay. So that's a very useful thing that convergence in LP implies for subsequence we have almost everywhere convergence. Okay. So convergence in LP does not mean you have yeah, it does not mean that you have convergence to something basically pointwise. So just I'm not going to go into as much detail as I did before, but the counterexample is exactly what we had for convergence and measure. So let's say I0 is 0 to 1. I1 is 0 to 1/2. Let's do, sorry. Yeah, this is fine. I2, I'll just do denominators of 3, so 1/2, and let's do sorry. Uh, 0 to 1/3. 1/3 to 2/3. Try to squeeze this in, etc. Then, right, so the integral sorry. I define Fn, no. So remember what Fn was? Just characteristic function of In. So so this here is just well, the measure In, and that's 0. Now we proved this in the video on convergence and measure, so I'm not going to repeat the proof. Well, this here does not exist for every x in 0 to 1. Okay. So yeah, convergence in LP does not guarantee pointwise convergence for any x whatsoever. In fact, this diverges, doesn't just not converge to 0, diverges for every x in 0 to 1. Okay. And so let's see. Right. So yeah, and as kind of usual, you don't pointwise convergence does not imply convergence in LP. There's a whole slew of examples you can come up with. So here's one example. We've done this before. Again, let's say E is 0 to 1. Emphasize that there's no issue with the domain being infinite. So let's say this is simply n if x is in, let's say, 0, 1 over n, or you could even do something like n squared. Let's say 0 otherwise. All right, so yeah, so the picture is kind of the obvious picture here. So it's 0 at 0 because 0 is not in this interval. So as this jump here, so we got 1 over n squared. So here, trivially, this is 0 for every x in 0 to 1. If x is 0, well, it's just 0. Oh, sorry, the limit is 0 for every x. And if x is bigger than 0, well, just pick n larger than x. Sorry, pick n larger than 1 over x, so 1 over n is smaller than x. So, right, that does it. So maybe I should, let me do this. Let me make black. Black is going to be what the graph is. While on the other hand, 0 to 1, fn of x, well, it's just the area under this curve here, and that's obviously n. N squared times 1 over n. Right. Yeah, you might grumble, well, this is unbounded. Well, if you want something unbounded, your domain has to be bounded, otherwise dominant convergence theorem would imply you have convergence to 0 in LP. Or so, yeah. Sorry. If you want to raise this to the p, this would be n to the 2p. So, or rather, so this would be n to the 2p minus 1. And certainly if p is between 1 and infinity, this is 0. And just simply make the 2 larger than 2 if you want p between 0 and 1. So not very subtle here.